Let's try and unpack this quantum computing.
Mm-hmm.
The buzz around it, it's just immense, isn't it? Promising these breakthroughs that honestly feel almost magical sometimes.
They really do. But yeah, beyond the hype, what's actually happening? What do you really need to get a handle on right now?
Exactly. So today we're doing a deep dive. We've got this fascinating snapshot of the quantum world, and it all kicked off from a discussion at NVIDIA GTC 2025.
That's right. It's mainly from a YouTube transcript, actually. Features NVIDIA's CEO talking with a whole range of leaders from different quantum computing companies.
Yeah, a fantastic lineup. It's like getting a front row seat to a pretty candid chat among the real pioneers, you know?
And our mission here is to pull out the crucial bits for you. Make it clear, digestible. We want to shed some light on where quantum computing is now, where it looks like it's heading, and, why it's worth your attention.
What really struck me from the source material was just the sheer variety of approaches.
Well, absolutely. And also, maybe surprisingly, how collaborative it seems, given how cutting edge and competitive it is.
So how did the specific discussion even start? It was something NVIDIA's CEO, Jensen Huang, said about timelines, wasn't it?
Yeah, that seems to be the spark. He was talking about how long it might take for quantum computers to be genuinely useful.
And maybe ruffled a few feathers.
That's probably fair to say. He drew a parallel between developing quantum platforms and the decades NVIDIA spent on GPUs and CEDA.
Ah, okay. Implying it's a very long road.
Right. So the natural conclusion was that broadly useful quantum computers were still quite far off. And apparently, as he sort of recounted with a smile, the quantum folks had some, let's say, spirited responses.
Which led to this forum. I mean, he basically invited them all to come and, well, state their case. Explain why maybe the timeline's shorter or the impact is nearer than he thought.
Yeah, it's pretty cool, that willingness to engage.
Definitely. And it gives us this unique window into what's happening right at the cutting edge.
And one of the first things that jumps out is just how many different ways people are trying to build these things. The diversity of the tech is incredible.
Totally. It's not just one path. You've got trapped ions, neutral atoms manipulated with lasers, superconducting circuits.
Topological qubits, which are still a bit further out perhaps, and even quantum annealing, which is kind of a different beast altogether.
It really shows how exploratory the field still is. Everyone's betting on slightly different horses.
So let's maybe touch on a few of these. We heard from Mikhail at Quera. They're using neutral atoms.
Right, neutral atoms trapped and controlled by lasers. He really emphasized how identical atoms are naturally.
Meaning the qubits are essentially perfect copies of each other.
Exactly. That, and they're well isolated, which apparently leads to really long coherence times.
Okay, and coherence time. Remind us why that's key.
It's basically how long the delicate quantum state lasts before it, falls apart and gives you errors. Longer coherence means more time to actually do the calculation.
Got it. More time, fewer errors.
Plus, he mentioned Quera can dynamically change how the qubits connect during the computation. That sounds important for error correction, building those more robust logical qubits.
Right, the error-corrected ones. Okay, then there was Chad from Rigetti Computing. Superconducting qubits. What's their angle?
His big points were scalability and speed. They build on silicon chips, so they hope to leverage all that semiconductor manufacturing know-how to scale up.
Makes sense. Use the existing infrastructure.
And because it's superconducting circuits, electrons, the actual operations, the gate speeds are incredibly fast, nanoseconds.
Wow. So potentially useful for things needing really quick calculations.
Yeah.
Like finance or complex simulations.
Could be. And he also mentioned a big jump in fidelity recently.
Fidelity meaning,
Accuracy.
yeah, how accurately the quantum operations perform.
Yeah.
Superconducting qubits sometimes struggled there historically, but he said they're now hitting 99 to 99.5% for 2 qubit gates. That's, getting up there with the other leading methods.
That's significant. And they have an open modular approach. Yeah, which I thought was interesting. They can apparently integrate components from other companies, kind of a best-of-breed idea. Fosters collaboration, maybe?
Interesting angle. Okay, next up, Ilias from Quantinuum. They also use trapped ions, like IonQ we'll get to, but what's their focus?
Fidelity seems paramount for them. They talk about hitting 9s and beyond, so really, really high accuracy, very low error rates.
Okay, pushing the limits on accuracy.
And their main goal seems to be scaling logical qubits, the error-corrected ones. They have ambitious targets, 50 this year, 118 months,
Wow.
and millions by like 2031 or 32. And they're very focused on applying this to really hard, real-world problems that classical computers just can't crack.
Application driven. Okay.
Yeah.
Then Loic from Pascual back to neutral atoms. What was their emphasis?
Scalability again. They highlighted controlling thousands of qubits already.
Thousands. Okay. Yeah.
And they also stressed the ease of using lasers for control. But a big part of their message was about engineering, taking it beyond the lab, building robust industrial products. They've actually deployed 4 machines globally already.
So moving towards real-world deployment. Then Peter from IonQ also trapped ions. He brought some history into it.
Yeah, he pointed out the science goes way back, like the first quantum logic gates in '95 linked to atomic clock research.
Interesting roots.
And a key practical point, their systems operate at room temperature in standard server racks. That's a big deal for deployment.
Definitely simplifies things. No massive cryogenic cooling needed.
Right. And they also see potential in networked quantum computers, distributed systems, and they highlighted their leading average 2-qubit gate fidelities. High accuracy again.
Okay, so lots of focus on fidelity and different practical advantages across the board. Now, Alan from D-Wave, that's the quantum annealing one, right? How's that different?
Yeah, it's a fundamentally different approach. Alan explained it's not really about executing a sequence of gates like the others.
So what is it about?
It's more like finding the lowest energy state of a complex system. Imagine rolling a ball on a bumpy landscape. It settles in the lowest valley. That valley represents the optimal solution, typically for optimization problems.
Okay. So tailored for specific problem types.
Exactly. And the argument is that it's easier to scale, number-wise, and less sensitive to certain kinds of noise compared to gate-based models. He mentioned some recent work like a useful calculation for magnetic materials and even a quantum proof-of-work idea for blockchain.
Interesting niche applications potentially emerging there. What about atom computing, Ben? Also neutral atoms.
Yes, another neutral atom player. They've hit systems with over 1,000 qubits.
Wow, the numbers are climbing.
Yeah. While keeping high fidelity and coherent operations. A key thing they mentioned was all-to-all connectivity.
Meaning any qubit can talk directly to any other qubit.
That's the idea, which can be really helpful for certain algorithms and, again, some error correction schemes.
Okay, that flexibility sounds useful. Then Matt from inflection neutral atoms again, but a different angle.
Very practical, market-focused. They're also aiming for room temperature operation, maybe for deployment out in the field eventually.
Right.
But their strategy is quite clever. They use the same core neutral atom tech to build high-precision clocks and sensors markets where they already make money.
So the clocks and sensors fund the quantum computing R&D.
Exactly. A way to bootstrap the really expensive quantum computing development.
Smart. Okay, John from Seek. Superconducting, but focused on the full stack. What's that mean?
It means they're building everything, from the qubits themselves right up to the control systems. They're focused on quantum computers on a chip, digitally controlled, very energy efficient, like nanowatts per qubit control, which is tiny.
Energy efficiency could be huge at scale.
Definitely. And they're aiming for a tight integration with classical chips, GPUs, CPUs.
So thinking about that hybrid future, what about Alice and Bob? Perrin? Superconducting too.
Yes, but they're really laser-focused on designing better qubits to start with, specifically for error correction. They have this cat qubit.
A cat qubit. Okay.
Yeah, the idea is it has some error correction built right into the hardware qubit itself. The goal is to make inherently robust qubits, so you need far fewer physical ones to make a reliable logical one. Quality over quantity initially.
That makes sense. Tackle the error problem at the source. Rob from Quantum Circuits, also superconducting.
Yep. Their philosophy is correct first, then scale. Similar idea, maybe. They have a dual-rail qubit design with built-in error detection at the hardware level.
Detection, not correction.
Detection first, yeah. So they can spot errors as they happen. The strategy seems to be get the basic building blocks super reliable, then scale up massively, aiming for a more efficient path to fault tolerance.
Okay, another approach focused on reliability. And finally, Pete from Side Quantum. Single photons. That sounds different again?
Very different and very ambitious. They're targeting million qubit scale fault-tolerant machines.
The million. Wow.
By leveraging silicon photonics. That's the tech used heavily in data centers for communication.
So tapping into existing mature manufacturing and infrastructure again.
Exactly. Potentially big advantages for manufacturing, cooling, power, connectivity, control, especially at that massive scale they're envisioning. It's definitely a long-term bet on photonics.
Wow. Okay, that's quite the whirlwind tour. It really does show the incredible range of ideas being tested. So the big question for you listening is, when does all this become, useful? And what does useful even mean here?
Yeah, that was a key part of the conversation. Someone suggested maybe thinking quantum computer is too narrow right now. Maybe quantum instrument or quantum processor fits better.
That reframing makes sense. It points to the idea that these machines, at least initially, probably won't replace your laptop. They'll be more like specialized coprocessors.
Working alongside classical CPUs and GPUs, like adding a new powerful tool to the box.
Exactly. And the early applications people are exploring seem to fit that hybrid model. Lots of talk about scientific discovery.
Right. Exploring complex physics, designing new materials or drugs, understanding systems that are just too hard to simulate classically.
And companies are already trying to solve specific, high-value problems for customers. Things like finding greener refrigerants or more efficient ways to make hydrogen or how proteins bind in biology.
I thought that IonQ example with ANSYS was interesting, modeling a blood pump and getting a real performance boost even now.
Yeah, and the 20x speedup they saw in a chemistry problem on just 36 qubits, that definitely makes you pay attention.
Or D-Wave's quantum proof of work for blockchain. Maybe niche, but potentially useful soon.
So yeah, maybe not doing your taxes on one yet, but in specific areas, they're starting to show value or at least serious promise.
But to get to that revolutionary stage, we need scale, right? Lots more qubits. And we need to nail error correction. Getting enough of those reliable logical qubits.
That's the huge hurdle. Going from today's physical qubits, which are noisy and error-prone, to the fault-tolerant logical qubits you need for the really big problems, that's a massive engineering challenge.
Yeah. I heard estimates like maybe 100 physical qubits just to make one good logical qubit right now.
Something like that, yeah. The overhead is significant. So if you need, say, 100 logical qubits...
You might need tens of thousands of physical ones.
Yeah.
And then you have to control them all, wire them up, integrate everything. Wow.
Which is why building these things on a chip, like classical processors, is seen as so critical for scaling, getting that density and integration.
And it sounds like progress is being made on error correction across all these different types of qubits.
Definitely. It's a major focus for pretty much everyone. They know it's essential.
Another really fascinating thread was the link between quantum computing and AI. How do those two fit together?
Well, the really exciting idea is using quantum computers to generate super accurate data, like ground truth data that you just can't get otherwise.
Data about what?
About molecules, materials, complex physical systems, things where experiments are hard or expensive, and classical simulations aren't accurate enough.
Ah, so the quantum computer does the really hard simulation.
Exactly. And then you use that perfect data to train a classical AI model.
Which could then maybe design even better materials or drugs much faster.
That's the potential. It could massively accelerate discovery in chemistry, materials, science, pharma, areas where good training data is scarce. Someone even mentioned the idea of quantum AI factories.
Quantum AI factories.
Okay.
AI agents working with quantum computers. That's pretty sci-fi.
It is, but the logic holds. Using quantum strength for specific hard calculations to power AI's pattern-finding abilities.
So let's circle back to the timeline question. Given all this, when might we really see transformative impact? Realistically.
Yeah, the million-dollar question, or maybe billion-dollar question. There seemed to be a rough consensus forming. Maybe around 100 logical qubits could be a kind of tipping point.
A point where quantum could start genuinely outperforming classical computers on certain important problems.
Potentially, yes. And many of the leaders seemed optimistic about hitting significant milestones, maybe seeing real impactful applications emerge towards the end of this decade, around 2030, give or take.
But it sounds like it won't be a switch flipping overnight, more like turning up the volume. Gradually.
That's a great way to put it. As the tech matures, as we find more problems it's suited for, its impact will grow. It won't suddenly replace everything.
Like the early days of classical computers, ENIACs and all that, people back then probably couldn't imagine laptops or the internet.
Exactly. The applications that ultimately become most important might be ones we haven't even thought of yet.
And despite all the different approaches, you mentioned collaboration earlier. That came through.
It really did seem like it. Even though they're competitors with different technologies, there's a sense of a shared, massive challenge and opportunity. Everyone benefits if the whole field moves forward.
And the trend seems to be towards integration, right? QPUs working with CPUs and GPUs.
Yes, that hybrid model seems dominant, plugging quantum capabilities into the existing classical infrastructure.
Looking ahead, what did they think next year's big topics would be?
More progress on error correction, definitely. Getting closer to robust logical qubits. Seeing some of those early use cases become more commercialized, advances in getting things integrated onto chips, new quantum algorithms maybe.
And hopefully more tangible examples in data centers and AI.
Exactly. Things you can really point to.
Okay, so wrapping this deep dive up, we've seen this incredibly vibrant field, lots of different shots on goal for building these machines.
Yeah, and the big focus now is clearly shifting towards cracking scalability and nailing error correction. Those are the keys to unlocking the potential.
And that synergy with AI that feels really powerful, using quantum to generate perfect data to train smarter AI, especially for science.
It's a really compelling prospect. But it's crucial for you, the listener, to remember, quantum isn't likely replacing your everyday computer.
Right. It's an extension, a new kind of tool for problems that are just impossible today, especially for understanding the fundamental rules of nature, materials, chemistry.
Precisely. Tackling the currently intractable.
So here's a final thought to leave you with. As this technology matures, what are the truly unexpected shifts we might see? Forget the obvious stuff. What currently impossible problem do you think might be the first to fall thanks to quantum computing? It's definitely a future full of fascinating possibilities.
Please click like and then subscribe. Also share this video with your friends. Thank you.